I'm Haruka Komiyama from Japan, and today I'll talk about the quantitative evaluation method for magnetoelastic coupling between surface acoustic waves and spin waves. Phonons are quantum of the lattice vibration, and magnons are quantum of spin wave, interact by magnetoelastic coupling in a distorted magnetic material. Magnetoelastic coupling is the effect of strain-induced modulation of the distance and angle between magnetic moments and its reverse effect. We focus on coupled system localized on the material surfaces, in other words, surface acoustic waves and spin wave in magnetic thin films. They also interact by magnetoelastic coupling, but interaction in thin films is smaller than in bulk. As a result, there are still few studies evaluating the coupling, and a universal understanding of coupling is insufficient. In terms of application, it is necessary to adjust the magnitude of the coupling as needed. In both the fundamental and application aspect, quantitative evaluation of coupling is essential. The coupling strength G is commonly used for the quantitative index of the coupling. Coupling strength represents the process rate in which one phonon is absorbed and one magnon is excited, or vice versa. However, the coupling strength G depends on multiple parameters. In particular, the mode volume of surface acoustic waves is an unknown parameter that can easily vary with device geometry or material. Therefore, coupling strength is not suitable as an index for quantitatively comparing the coupling between different studies. Instead of coupling strength, we focus on the constant BD, which only depends on the material. B is the magnetoelastic coupling constant, and it has an energy density dimension. And D is a dimensionless constant that determines the magnitude of strain. Because BD depends on the membrane quality or the deposition method, determining the value analytically is difficult, and using bulk literature values is inappropriate. In this research, we establish a method for experimentally evaluating BD by combining electrical measurement and optical imaging measurements. Here is an optical microscope image of the device. The substrate is lithium niobate, which has piezoelectric effect and is typically used in surface acoustic wave devices. The yellow part is made of 5 nanometers titanium and 18 nanometers gold. It consists of an electrode that excites surface acoustic waves, or IDT, and a black mirror that confines surface acoustic waves. This surface acoustic wave resonator was fabricated by applying EV lithography, magnetron sputtering, and liftoff. From electrical measurement, we confirmed that this device had resonance frequency of around 800 MHz. Using the same fabrication process, we deposited 15 nanometers nickel and 2 nanometers tantalum in a surface acoustic wave resonator. First, we performed electrical measurement on the device and evaluated the conventional parameter coupling strength G. Here is a measurement setup. A static magnetic field HDC is applied in the plane at angle theta, and the reflection coefficient S11 was measured using VNA. This figure shows the frequency spectrum of the amplitude and phase of S11 measured when a magnetic field of 15 millitesla is applied at an angle 45 degrees. You can see the amplitude dip and phase rotation around the resonance frequency of the surface acoustic wave. And here indicates the surface acoustic wave and spin wave's resonance frequency. Previous studies evaluating the coupling strength use magnetic field conditions in which surface acoustic wave and spin waves frequencies match. In our device, The frequency of spin wave coincides with the frequency surface acoustic wave at 800 MHz only when the magnetic field is low. However, preliminary experiments confirmed multi-domain behavior in such low magnetic field. On the other hand, under the conditions of a single magnetic domain, the frequency of surface acoustic wave and spin wave are separated by several gigahertz. Even under these resonant conditions, we evaluate the coupling strength G as 5.67 MHz by fitting with an appropriate model function. The coupling strength G just evaluated can be expressed in the following formula. Multiple parameters determine G, but they can be divided into three groups. First, BD, the parameter we are interested in, and then, shown in the green area, the non-constants determined by material constants such as magnetization saturation MS or experimental conditions like angle theta. And then the surface acoustic wave mode volume VSAW. The fact that VSAW exists in the denominator of G indicates that the energy density of phonons increases as the mode volume decreases, leading to increased interaction with magnons. The VSAW can easily change depending on the device geometry or material. Coupling strength G, which includes VSAW, is unsuitable as an indicator for quantitatively expressing the coupling system. For quantitative evaluation of the coupling, we identify VSAW from optical imaging of surface acoustic waves. The spatial distribution of surface acoustic wave was obtained by observing the modulation of the reflected light path according to the surface tilt using the photodiode and VNA. First, I show the amplitude and phase map of the signal scanned within this white frame. In the X direction, amplitude peak positions have an interval of 2 micrometers, and the phase inverts by pi every 2 micrometers. In the Y direction, the nickel film does not have the phase node. So standing waves with wavelengths 4 micrometers or fundamental waves were confirmed in the nickel film. So I have confirmed the mode. We now evaluate the surface acoustic waves mode volume. The decay of amplitude shows the length in Y direction is about 100 micrometers. Similarly, to find the length in the X direction, scan along the blue dashed line. We obtain the length seeping out from the edge of black mirrors by the fitting. When the distance between the black mirrors is also taken into account, the effective length in the X direction is 578 micrometers. Assuming that the surface acoustic waves is localized in the Z direction over a distance of about one wavelength, VSAW is obtained as 2.2 times 10 to the minus fifth power cubic meters. The formula for G is shown here again. Substituting the literature values and experimental conditions into the green part, and the value evaluated from the electrical measurement into the couple strength G, and the value obtained from the optical measurement into the previously unknown surface acoustic wave mode volume VSAW, we obtain the constant BD as 8.1 times 10 to the fifth power joule per cubic meters. Quantitative evaluation of the coupling is possible by applying this method to a BD, evaluation device, on the same substrate as the device for research. Since the spatial distribution of surface acoustic waves varies depending on device geometry and materials, confirmation of surface acoustic wave modes and evaluation of mode volume by optical imaging is essential to progress research quantitatively. And one problem that has prevented the introduction of optical imaging is that the optical spot diameter limits the maximum frequency of surface acoustic waves to about 1 GHz, making them off-resonant with spin waves that has frequencies above GHz. But this study shows that it is possible to evaluate coupled systems even if they are off-resonant. To summarize this study, we combined electrical and optical imaging measurement to evaluate BD. And BD is a more practical and universal constant to quantitatively indicate the coupling between surface acoustic waves and spin waves. Thank you for your kind attention.
Thank you for the interesting talk. Now the session open for the discussion. We can take one question. So please go ahead. Any short question?
Hi. Yes. Can you hear me?
Yes.
Hi, Haruka. This
Hi.
is great work. So I was wondering, what are the most ideal conditions you found for the the coupling rate between the magnon and photon in the system that you've been studying?
So you mean you're wondering the magnitude of coupling strength between phonon and magnon, or the research technique?
So it was my understanding that the BD term was sort of what determined the coupling. Can you maximize this in some way or control it?
Mhm. In my thoughts, of course, material is very important, and other point is surface acoustic wave mode volume, or VSAW in this talk. So to repeat, VSAW is can change very easily by device geometry. So if you want to maximize the coupling between phonon and magnon, you have to change device geometry or material mass.
Okay, all right, that's okay. That explains things a bit for me. Well, this was a great talk. I can't say that enough. Thank you.
Thank you.
Okay, so thank you, Harika, for your nice presentation.